Hi everybody, welcome to lecture 2 of video coding. So last time we saw that we can use Python and OpenCV to capture a picture, and today we want to continue and use it for capturing video. So going back to OpenCV, we have this command in Python, cv.videoCapture, and the argument here, the 0, in this case is the default camera 0. So this is the camera, the only camera if you have only one camera, or if you have multiple cameras then you can choose. Right, so in my case I'm actually having two cameras, so here's my other one. So if I want to use it, I would need to change it to 1, for instance. Yeah, so that's very convenient, also if you have more than one camera. So then cap is now our object, right? So cv2 is the library, and video capture to camera 0 now generates this object cap, which again has a few functions which we can call. Right, and this cap then also contains a pointer to address this camera. And we can read a frame of this stream as in this example here. We have cap.read as a function, and this function now accesses the webcam and returns a frame, and if it was successful then this redval, this return value, which is Boolean, returns the true. Right? It's true if it was successful, and it's false if it was not successful. For instance, if for some reason there is no camera, or camera is not operating. So this can be used in our program to then test if we were successful, and otherwise give out an error message. Yeah. So frame now contains the frame that we just got from the camera, and with imshow, cv2.imshow, we can now display this frame, basically as we did last time with our photos. So here we generate a frame with a name frame, and it displays the frame that we just captured. And this is then displayed in the frame, and in this time when it's displayed, the function cv2waitKey waits for 1 millisecond for a key, and actually keeps querying the keyboard. So the window is opened by cv2imshow, and it does not open without the wait key, so they are actually connected, and it's kept open for as long as prompted by wait key. The argument of wait key tells the function how many milliseconds to wait for a keystroke. So in the example it was 1, so 1 millisecond. And the function cv2waitKey is only active when the associated window is active, which means it's in the foreground and before you clicked on it, right? So you clicked on it, and basically you can tell if the top bar of the window is highlighted. And in this case, it actually forwards the keystroke that you make on the keyboard to the program. So only if this window is active, otherwise not. So when we do this in an infinite loop, we get the live video from the camera in the window. So basically one frame after the other. So here's an example program. So we start with importing cv2. Then we access the camera 0. And now here we have an infinite loop with while true. So in the beginning we read a frame from the camera, then we display this frame, and then we query the keyboard. So we wait for 1 millisecond to see what key was pressed, and then we check it. So here we have a template, sort of a template, which only keeps the last 16 bits, the last 8 bits. So FF is a hexadecimal, so each F represents 4 bits. So then FF is 1 byte or 8 bits, and this is the logical the binary AND operation here. And if you have an AND operation with a 0, then the result is 0. If you have an AND operation of some bit with a 1, then the output is this 1 bit. So in effect, this sets, if you have more than 8 bits, then this sets the leading ones to 0, and the rest is kept to the original state. And then this is compared to the ASCII code of Q. So in this case, we want to have Q the function of quitting the window. So if we hit the key Q, then we want to program to end and exit. So if the key we press has a ASCII code which is identical to the ASCII code of Q, then it breaks the loop. It ends the loop. So break basically quits this infinite loop. And then it just releases everything. So here capture released and CV2 closes all windows. Yeah, and then we can store this program as videorecdisp.py, for instance, and then start it from a console or terminal window with the command python videorecdisp.py. So we can try this now. So here is a terminal window, and first let me open the program because I have to change the camera. So gedit video recdisp.py. So this opens my gedit editor, and here we can see in line number 6 we have this camera access, the pointer to the camera, and now let me change this to 1 because number 0 is already busy, and then we can start it from the same terminal window, but instead of opening it with an editor, I'm going to execute it with Python 3. So let's see what happens. Yes, so here you can see a picture of me, so that works. And now I can hit the Q, and it finishes. So this is exactly what it's supposed to do. Yeah, so basically now you have the possibility to have a live camera feed basically to your display. So a practical application could be, for instance, a pipe camera which you can use for inspecting narrow spaces like in pipes. Yeah. So the following example shows the contents of the upper left pixel of the video at the start of the program. So this is actually nothing useful, just for inspecting what's going on. So here in the beginning the same. Here we read one frame and then we just print pixel number 00. So here you can see vertical, horizontally, coordinates 0. And then the last one, remember, was the primary colors. So we expect 3 outputs. And what you see here is, for instance, 480. Image format is first 480, 640, and 3 primary colors. So this is actually the format from the camera, which is printed here. So frame.shape. So this is VGA, this is basically the standard. If you don't change it, it's always this size. And here you can see pixel number 0. So here we can see this array. This is blue, this is green, and this is red. And we have a data type of unsigned int 8. So 8 bits per primary color unsigned, which means we have a value range from 0 to 255. So we can see this is true. And we can actually try this. So here we will see probably that it's not working because I didn't change the camera. Let me try it. Yeah, so here it says, it gives an error message. So I need to first change the default camera device, or the camera device, gedit. So I'll change this to 1, close it, and execute it again. So you can see I'm executing. And indeed, we get the image format, 480, SIG by 640, 3 primary colors, and here are now the values of the primary colors. So in this case it's 126, 109 and 113. So this is different from the values in the slide because of course the camera now has a different image. Okay, so this shows you the basic format that we get from the camera. Yeah, and you notice the colons here when we display the pixel, the primary colors. The colon means basically all the indices of this dimension, so from the beginning to the end. So in this way we can also address an index range, for instance, start colon end. For instance, 0:3 addresses the indices 0, 1 and 2. Right, and not the last value. So, yeah, in our case, this is identical to 0:3. Right, because we only have 3 indices in this case. Yeah, so at the output, we therefore do not get a single value, but a special array with the values of the 3 primary colors in the order BGR, blue, green and red. So in our example, red had the value 146, green 167 and blue 35. Yeah, and as I mentioned, we have this number format unsigned int 8, unsigned integer, and hence the number range from 0 to 255, which is 2 to the 8th power minus 1. Yeah, and then I have another demo which now displays the different primary colors, R, G and B, in different windows. So first let me open it again, copy, and open it with gedit. So here you can now see the program. So it's very similar to the previous ones, but now we have more open windows. So actually I opened 4 windows, as you can see here, named original, then the blue component, green component and red component. Here in the infinite loop, we first capture, we read a frame, and then we just go through the components. So first is the original. So this is what we just did, color frame. But now we also display the individual blue, green and red frames as monochrome images, so just as intensity images. So they don't appear in color, but as intensities. So then you can see which intensities dominate, for instance. So again, I need to change the camera here, move it to 1. And I can execute it. So Python 3. So I point the camera towards me. Yeah, so here you can see the original is this, right? And then you can see the 3 components. Red has more bright values, so here this is brighter because the components for red are bigger there. Then you have the green component, and you can see, for instance, my face appears darker, but the background walls here are about the same, which means it has as much red as green, and this is also a property of white, it has all the colors equally. And here you can see the blue component. You can see my face contains almost no blue, because it appears darker, but then here the wall still is roughly the same. So yeah, that works. So here you can also see the frame duration. This basically shows how fast the computer captures the frame. So Q, let me quit. First I need to activate one of the windows, the frames. Then I can press the Q, and then it stops. Yeah. So here you can see start time before it captures, and then it displays, and then here I have end time, and this is what it displays, end minus start time. So basically what you saw was basically the duration from capturing to displaying. And this is actually something that depends on the speed of your computer. The faster your computer, the shorter the times will be. Okay. So this is what I just did. And this is also a nice demo. If you hold a red paper in front of it, then you can see that it's becoming brighter in the red component. In this case it was my face, which is more reddish. And you can also do it with other colors. If you hold something blue in front of the camera, then you will see that the blue region will appear brighter in the blue component window. So since wait key now has a wait time of only 1 millisecond, this is actually shorter than the computer needs to display, so it will basically show as many frames per second as the hardware allows. And this leads us to a simple encoder-decoder framework. So this is useful for making your own video coder and decoder. So we saw we have OpenCV, which is basically used to capture and display video. So you can use this framework for building our own coder. So the Encoder Framework simply takes each frame of our video sequence and appends it to our video file for now uncompressed format in a text format. So this is basically the starting point. It takes the video and then just stores this video stream into a file, uncompressed. And we will see this file will be huge. And it's actually even in a text format so that we can actually see it in an editor. And the decoder framework reads one frame after the other from this file and displays it back on the screen. So this is basically what will become the video decoder. So here's the setup. Here we have the camera. Then the encoder is what we still need, and then it stores in the file. And here the decoder takes the file and then decompresses and displays in the file. And during the course, you are supposed to add more and more functionality to this framework such that the video file becomes smaller and smaller, because video coding is supposed to compress. So the encoder framework is in the file videoencframework.py. And here you can see it. So it starts as just in the examples that we just saw. It imports NumPy and OpenCV. It also imports Pickle. And since you're all using Python 3, we import Pickle, the name Pickle, otherwise it would be slightly different. And Pickle is used basically to convert structures, objects in Python to file without us having to take care of formatting. So that's convenient, especially when you do video. You have a sequence of images. Images have certain formats. Then Pickle takes care of all the formatting information. So it's convenient for us. It doesn't have to be. We can also do it differently, but then you have to take care of all the formatting information yourself. Right. So then it writes into the file videorecord.txt. And here you can see how it works. So in the beginning, it captures our camera. And then we open our file in which we want to store our information, the video. So it opens this file with this name, videorecord.txt. in write binary format. So it's a writable format and binary. And if this file exists, then it's automatically deleted. So be careful using it. So in this case, we just take 25 frames. So I have a loop here where n is in the range between 0 and 24. And we then capture from the camera. Here we have the camera capture. And if return is true, then we continue. Otherwise, we have a problem. So then we display the frame. And here we could add now compression, for instance. Right? So we could reduce the data rate, but in this case, we just copy the frame and cast it into type uint8, which in this case doesn't really make a difference. And then we just pickle dump it to our file. And then we have our wait key argument here, which lets us break if we hit the key Q. Yeah, and if the camera is not present, we also break. And then we release the camera and close the windows. Yeah, and then we can start it. So here I also open it to change the camera. Gedit. So again, I have to set this to camera number 1. And then I can now execute it using Python 3. Python 3. So let's start it. And now it should do something. Yes. So that was quick. Yeah. And again, observe that it only takes 25 frames and basically still as fast as the computer allows. So we didn't specify any frame rate, right? So the camera just takes frames, and then here just waits for one millisecond, and then it goes on. So basically it takes the video as fast as it can. So that is basically one of the drawbacks of this framework. So that is something that we also need to fix. Give it a defined frame rate. So yeah, this is what I just mentioned. Pickle is convenient for us because it can easily allow us to store a tensor, like from our video, into a string, a serial string, which then can be easily stored in a file, and vice versa for the decoding framework, which we can then start with a corresponding file. So here we take a look at it. Again, opening our editor, gedit. So here you can see it. So in the beginning, we open this file that we just wrote, this time in mode R for read. And then we have this infinite loop, which reads from this file. And basically every time we use pickle load, it reads a frame. Just like in the encoder, every time we use pickle dump, it stored a frame. So when you go back to the encoder, you can see in this loop, for each frame we applied pickle dump. So each time we apply pickle dump, it takes this frame reduced and stores it to the pickle file f. Here we do now the opposite. We have this loop, and every time we access pickle load, it loads a frame from file f. So basically here in reduced we again have this frame back. Right, and here we could do the decoding. In this case we just do the copying as a placeholder. So then we have the frame deck, and it displays the frame deck. Here using imp show. And again, here we have the possibility to quit with Q. Otherwise it will just read as long as there is content in the file, and then It will just stop when there's no more to load. So then we can try it. So here I don't need to set any camera because there is no camera, it's just display. So going back to my terminal window, here I'm saying Python 3, and then it automatically loads from the file that we just generated. I need to have Python 3 here. It has to be Python 3. This is for Python 2, so I need to actually change it. Here this should be import pickle, because for Python 3 they changed the name for some reason. So let's try it again. There's still a problem with Python 3, it seems. Let's see what it does. Can't invalid start byte. Interesting. Yeah, this error message doesn't really say so much. It's line number 15, so it's this pickle load here. Let's see what we have in this file. So copy, and then say ls-l for long, and the name. And here you can see now, here ls means list, right? So it lists all file names which have of this name, and -l means extended information, long information. So here you can see video record, time of the creation, and here's the size. So the size looks reasonable, quite big, as you can see, even though it was just maybe a second. So it's not empty, so that's good. Then it doesn't really explain what went wrong here. Let me go back. So this looked reasonable. Interesting. So this shows you what can go wrong. Dec inc. No. Interesting. Pickle load F. Codec can't decode byte in position 0. Invalid start byte. So this sounds like there's a pickle version problem. I see. Yeah, I guess I need to fix that later. So this is actually now a case for debugging, and debugging is actually something, to be honest, which usually takes more time than programming itself. Right? Usually you have an idea about a program, you write the program, and then you find it's not working. And then you have to closely read the error messages and try to find out where the error comes from. And then in this way zoom into what exactly is wrong and then fix it. So that's a systematic, basically detective work to find out what was wrong. And it can happen that some versions like Python 2 and Python 3 are not compatible, and this is one of the common errors that you encounter in programming, that different versions of different libraries don't play together. And that's also why it's important to always keep your system up to date on the newest version. And even then it can happen that something doesn't play together. So let's first ignore it. So here we just saw that 25 frames that we have, which is basically 1 second of standard TV quality, VGA, in our simple uncompressed framework results in a size, file size of already over 40 megabytes. So let's see, in our case it was, how much was it? Here it is. So when I say -LH, we get a human readable form. So we actually have 22 mega bytes, so it's actually somewhat less than those 40 megabytes for some reason. Yeah, maybe that's where something is wrong, I don't know. So in any case, it's huge, right? 1 second, not even very good quality, and 40 megabyte is too much. And this basically is the point for compression, right? We cannot really have 40 megabyte for each second. So here's a short computation. Just assume our short video clip of 1 second duration with 640 times 480 pixel resolution and 25 pictures per second and 8 bits per pixel in primary color. Then we have 8 times 30 times 640 times 480 bits per frame times 25 frames per second. This results in 184 megabits per second, or about 23 megabyte per second. So this is actually where we see the 23 megabytes. So this is actually what we just saw. It just doesn't quite fit to this number here. But it's not so important. So this shows you it's too much, right? So, oh yeah, our framework has about twice as much because it uses text format. So this is actually what could have changed in Python 3. I think in Python 3 the pickle library now compresses more efficient. And this is why we get less than the 40 megabyte that we saw above. Yeah, so this is also one of the difference between different versions of Python. So actually pickle changed between Python 2 and Python 3. Yeah, so now imagine we have HD video. This would be about 2 megapixels per frame, right? So it's actually much more. So this is a particular problem if you want to stream a video to transmit it. DSL usually has maximum maybe 16 megabits per second, or maybe 50 if you're lucky. But it is already possible to stream HD video over DSL. This shows the power of compression, right? So even though uncompressed would not fit, but compressed does fit, right? So that shows how important compression is. So for instance, with good compression, HD video can be transmitted with about 4 megabits per second, down from about 480 megabits per second uncompressed HD. Right. So this shows it's really important. We need it. So how does this compression work? So there are two basic principles. First is the irrelevance reduction, which is basically removing all information which the eye cannot see, because in our case the eye is the receiver. And then the second principle is the redundancy reduction, removing all information which appears multiple times in our bit stream. So both are necessary to obtain the most compression. So we need to apply both. So first, the irrelevance reduction. This principle looks at the receiver of our data, in this case the human eye. We only need to transmit information that the eye can observe or detect. But observe that for this we need assumptions about the context in which the eye sees our signal or video. For instance, the viewing distance, the size of the monitor, the brightness of the monitor, and of the surroundings. For this reason we have specifically determined viewing environments for perceptual measurements. So these are assumptions like for typical use. And if we violate those assumptions a lot, then things don't work as well anymore. So you need to keep in mind that every time you do irrelevance reductions, there are many assumptions in it to which we need to stick, otherwise it might not work. So what are the usual properties of the eye used for compression? So for that we need to look at how the eye is looking like inside. So here you can see on the left hand side is the lens. Then on the right hand side we have the retina. And on the retina we have light sensitive cells of different types. So there are two major types. First is the rods, which are very light sensitive, but they are not color sensitive. So they take any light that comes in of whatever color. So basically, every light particle which comes in is then converted into a signal into the optic nerve. But then there's also the cones. The cones basically have three subtypes for the three primary colors: red, green and blue. And this is also the reason why we have primary colors, because they come from those three subtypes of cones that our eye has. If our eyes had only two subtypes, then we would have only two primary colors, as the case, for instance, for cats. If we would have more subtypes, like birds, then we would have 4 or 5 primary colors. So this is where actually our primary colors come from the three subtypes of cones. Yeah, another important distinction is that we have about 110 million rods, the most light sensitive receptors, but the color blind ones. So they are sensitive to intensity or luminance, not color. And about 6 million cones which are sensitive to colors. So the 110 million rods corresponds then to a camera of 110 megapixels. So quite a lot. But then we only have 6 million color sensitive sensors, which means which corresponds to a camera of only 6 megapixels. So basically we have a mix of both. Yeah, so the cones are sensitive to the electromagnetic wavelength spectrum of the three fundamental colors: red, green and blue. So basically they are acting like bandpass filters to the specific wavelength range of those three fundamental colors. And you can actually plot those bandpass filters in this following diagram. So here you can see it. So on the horizontal axis you have the wavelength, and vertically you have the sensitivity, and this basically can be interpreted like band passes. So basically here you have where you see the peaks, this is the pass band, and when it goes down, that's the stop band. Right here you have stopping, and here in the middle you have passing. And this is from the book Video Processing and Communications by Yao Wang and Jörn Ostermann and Yakin Xiang from Prentice Hall. So I like this picture because it's more quantitative. So you can actually see the different sensitivities in the different heights here. So this also shows that in the middle the green cones have the highest sensitivity, because here the peak is the highest. It has the highest relative sensitivity. Then the red one on the right is broader, so it's more wideband, but it's also lower here in the peak, so that means it's slightly less sensitive. And then a specialty here is the blue one. This is actually increased, enlarged by a factor of 20. So in reality it's a factor 20 lower. So this shows you that the blue cones are not very sensitive in comparison to the other two. So it's much lower here. And you see another specialty here. There's another side lobe here of this filter for the red wavelength. So here you can see the red cone. The bandpass of the red cone goes down, and here it has a ripple here in the blue region. And this is kind of interesting because this ripple here is exactly on the slope of the blue cone filter curve. And this basically makes possible for us to distinguish between blue and violet, right? So if you have, say, wavelength coming from the light, and this wavelength is in this range here, on the upper part of the blue bandpass, on this range here, the lower wavelength part, then you would only have output from the blue cone, because the other ones, they already have it in the pass band, in the stop band, I mean. Except for this red one. Here in the red one, it has sort of this side lobe, and that means it becomes active when we go from the pass band of the blue and approach the stop band. Then this red cone becomes active again, and that means we can distinguish the color of blue from purple or violet. So here this range of wavelength is then seen by us as purple or violet because of this side ripple here. And I've read that this side lobe here actually appeared in mammals after the dinosaurs died out. So the dinosaurs had more primary colors, just like birds today, like 4 or 5. And mammals during the time of the dinosaurs were night-living creatures. For them, color was not so interesting, so they were losing 1 or 2 cone types, because they were mostly hunting at night. And then when they were becoming day-living creatures again after the dinosaurs went extinct, then this is kind of like giving us a little bit more detail at this lower wavelength range, the detail between blue and purple or violet. So it's not as good as birds, but still better than just having 3 cones. Yeah, so this is what I just said. We have this interesting side lobe of the red cone in the blue range. Yeah. Right. So this is what I just said with the dinosaurs. Yeah, and birds are descendants of those dinosaurs, and they still have those 4 or 5 type of color-sensitive cones. So they have much better color resolution as we do. And for birds, it's also important for finding their foods in different kinds of flowers, for instance. Yeah, so we perceive different colors by different mixes of the relative outputs of the 3 types of cones. Right? We can see many more colors than just 3. And this is because our brain creates the illusion of different colors out of different mixes. And this is shown here in this triangle. So this has just 2 dimensions despite having 3 types of cones, and this is because we normalize everything to be summing up to 1. So red plus green plus blue is always summing up to 1, and this basically gives us a subspace in the 3-dimensional space of possible outputs of the 3 different cones. So basically you can imagine this space here being a subspace where the sum of the 3 outputs is 1. Yeah, so you can imagine the horizontal axis of this diagram being the output of the red cone. Then the vertical axis would be the output of the green cone, and then the rest of the sum to 1 would be the blue output. So in this way we get all possible colors that we can see. And here you can see on the boundary of this triangle shape, we have the colors that pure wavelength would appear. So if you have, for instance, a laser light is basically just a single wavelength, then this laser light would give us colors which are located here on the boundary of this kind of horseshoe shape. Right? These are pure colors. And you can see here, we always have mixes, even if we have pure colors. So we start here. Here we have 700 nanometers wavelength. And you can see the red cone is excited by a factor of 0.7, a little bit more than 0.7 here. And we can see green here is excited maybe 0.25. And the rest would be blue, right? 0.05 for instance. And then if we go up in the frequency or go down in the wavelength, you can see here the output of the green cone decreases because we go right to left until we reach the green point here. And when we reach the green point, we have the maximum of the output of the green cone here. So we have 0.85 roughly here at this point, and just a little bit red. So here we would have 0.05 red. So that means the rest, about 0.1, would be blue. So then if you then continue, reduce the wavelength, then we still have less output on the red cone, and going more to the left until we reach the minimum here in the blue-green area. Right? But then if you further go down in the red, in the wavelength, the red increases again. So here we can see we go now towards right, which means the output of the red cone increases again. And this is the effect of the side lobe, right here, this increase of the red output going towards higher frequencies or lower wavelength. So here you can see as an effect we have this purple-violet colors coming out. And this diagram is also very interesting for color mixing and also for drawing the color of the so-called black body. Right? So black body basically, as the name says, is basically like a black metal disc, for instance, or metal sphere, or just imagine you have some metal which you heat up. So metal itself does not reflect any light, that's why it's black. So we can imagine we painted it black. So it only shines itself when you heat it up. So here you can see under which color this metal will appear at different colors, at different temperatures. So here the numbers that you can see correspond to the temperature in Kelvin. So here it is 2000 Kelvin, and Kelvin is basically the same as Celsius, except that it starts counting at the absolute zero. So absolute zero would be minus 273 Celsius roughly. So 2000 is roughly the same as Celsius. So here 2000 Kelvin, we have this orange light, and then if you go up here it's roughly 6000 Kelvin, we get a white point, we get really white light. And then when we go up even more, it becomes a little bit more violet white. And this is interesting because this is related to traditional light bulbs. In light bulbs we have this little filament. Current goes through the filament and heats it up. And this filament is out of very temperature resistant metal, so that it can be heated up to 1000 or 2000 Kelvin without melting. And this is the principle on which light bulbs, traditional light bulbs, are built on. So here you can see when we have 2000 Kelvin, which is about the maximum we get here from light bulbs, we get orange color. But that also means that light bulb cannot give us daylight white. So daylight white would require something like 6000 Kelvin. But there's no metal which lasts at 6000 Kelvin. 6000 Kelvin, basically any metal evaporates. So that doesn't work. But actually the sun has about 6000 Kelvin on its surface. So that's why we see the light coming from the sun as white, because our eyes are adapted to sunlight as pure white, daylight white. So this is this point. Sunlight basically appears as daylight white because our sun has this temperature. So basically the sun is also a black body, except that it appears white because it's so hot. Right. So the sunlight here has this 6000 Kelvin color temperature, and that's because that's the temperature at its surface. Yeah, and this also shows the benefit of LED lamps. LED lamps don't need to be heated up. They have certain semiconductor structures that emit light from their semiconductors without heating up. So just giving those semiconductors a certain structure allows us to emit light at a light temperature of 6000 Kelvin. Right? So that's also why LED lamps are very suitable for studios, because they give you daylight white. And that's also why it's good for lighting indoors, because LED lamps, you can actually choose what color temperature you want to have. Maybe during the day you want to have daylight white, and during the evening you want to have something more reddish, which is reminiscent of a fire, for instance. Yeah, so LED lamps give you this flexibility. Yeah. And interesting is also when you compute the frequencies of light. For instance, take 500 nanometers of light, which is in the green area. So this is the passband of our green rod. We can compute now the frequency. So the frequency is obtained by taking the speed of light, or the speed of electromagnetic waves, and divide it by the wavelength. So here the speed of light is 300,000 kilometers per second. Here our wavelength is 500 nanometers. And if you type it into a pocket calculator, we get 600 times 10 to the 12th hertz, which is about 600 terahertz, or 600,000 gigahertz, which is a lot, especially when you compare it to satellite TV, for instance. Satellite TV is the highest frequencies which we use for TV, and they use frequency in the range of 10 gigahertz. And now we have 600,000 gigahertz. So that's 60,000 times as much. And since the bitrate we can use in a given channel, this is usually proportional to the center frequency. So that also means the bitrate we get at 10 gigahertz, we get about 60,000 times as much if we use light. And that shows the possibility of fiber optics to transmit data or videos, for instance. So that's why fiber optics gives us the highest data rate. Yeah, so back to the eye. Those about 6 million cones are unequally distributed on our retina. They are highly concentrated in the center of vision, the fovea, and become more sparse towards the periphery of vision. This is unlike typical digital cameras, which have equally distributed sensors. So this is actually one difference to cameras. Also observe the big difference in the number of only intensity or luminance sensitive rods. There are 110 million rods, but only 6 million cones. This means that the eye is much more sensitive for spatial changes in intensity or luminance than for spatial changes in color. Right? Also different important observation here. This is also an important principle in video coding, where color is usually encoded and transmitted with less spatial resolution. So that saves bits, a lot of bits actually. For instance, the color information is subsampled by a factor of 2 vertically and horizontally, so total a factor of 4. They are also unequally distributed with less density towards the periphery of vision, but with the exception of the fovea, where there are only cones at high densities, with no space for rods left. So in the center of vision, we have only rods. So in the center, we really see detailed color information, but at the same time, since the rods are left in the center of vision, it's less sensitive. And you can observe this, for instance, when you look at night at the stars and try to look at weak stars. So if you see a weak star in the night sky and then try to focus this weak star, all of a sudden it disappears in the center of your vision. So nothing is wrong with your eye, it's just how our eyes are built. Right? In the center of vision, they are less sensitive. So you see the weakest stars just slightly off the center of the sharpest vision, which is kind of disappointing, but when you have cameras with long exposure, then you can also see those dark skies more detailed. Yeah, so rods are much more light sensitive than cones, hence they are the main contributor for our night vision. Unlike the cones, which are tuned to our sunlight, our rod's spectral density sensitivity is tuned to the spectrum of our moonlight. So that's also kind of interesting. Our cones, the color sensitive versions, are basically tuned to sunlight. They see the sun as white. And also the spectral sensitivity of our rods is tuned to the spectrum of our sun. And similarly, the rods, which are mainly for night vision, or they are the only ones active at night, they are tuned to the spectrum of the moon. So the moon spectrum is actually a little bit more blue shifted compared to the sun, and this is actually what we also see at the sensitivity of our rods. So you can see our eyes are perfectly adapted to our natural light environment at day and at night. Yeah, so we see that the eye has a much higher spatial resolution, corresponding to about 110 megapixels for luminance, the intensity or black and white picture, than for chrominance or color, corresponding to only about a 6 megapixel camera. So how can this be used in video coding? So first, for luminance, intensity, and chrominance, color can be encoded differently. For that, we first have to separate the two, because usually cameras only have color sensitive sensors similar to our cones, but they don't have intensity sensors like our rods. So maybe that's also a disadvantage, or maybe this is also why digital cameras, especially when you take videos, they are much less sensitive than our eyes. So taking pictures, you don't see that much of a difference, but when you take videos, often digital cameras don't reach the sensitivities of our eyes, and the reason is our very sensitive rods. Right. So in any case, since our cameras don't have rods, we need to create an artificial rod output. Maybe at some time in the future we will have digital cameras which do have technical rods, but so far our cameras only have the three primary colors, red, green and blue, which correspond to the cones. So to obtain the artificial rod output, we need to apply our color transformation. So we take the three primary colors from our camera, red, green and blue, and then apply a transform to it, which you can see here. So the intensity Y, so this Y now corresponds to our rods, is computed as 0.299R, and this factor comes from the relative sensitivity of our red cones plus 0.257G, the green cones, you can see here. Indeed, as we saw in this diagram that we just saw, this number is higher because the green cones are more sensitive. And here you can see blue has the lowest factor because in our eye the blue cones are least sensitive. So this corresponds to this factor here. So these factors actually come from the different relative sensitivities of our eye's cones. Yeah, so then Y is now sort of the artificial rod output that we generate. So this is one output, but since this also contains part of the information of the other three, we just need two more components to get the complete information. So then we compute a color component CB, which is 0.564 times blue minus y. So this is then the resulting equation here. And here is the color component CR, 0.713 times R minus Y is this one here. And these factors here now come not from the sensitivity of our eye, but just to keep CB and CR in a range which is convenient for digital processing. Right. So altogether can be written in a matrix, and this matrix also shows you that we can converge back and forth because the matrix is invertible. So after the camera, which gives us the RGB components, so each pixel RGB components are multiplied with this matrix, and then for each pixel we get the new vector Y, CB, CR. So now Y contains our artificial rod, and CB, CR is basically then the type of color that we have. Similar to the color triangle diagram which we saw before, where we also have only two dimensions to describe the color type. Now we have something slightly different, CB, CR, but CB and CR also describe the color type, and Y is then the luminance, the intensity. Yeah, so what I just said, CR and CB are the color or chrominance components, which is normalized versions of U and V, which we know from analog TV, for instance. And they are normalized such we can store the value within a fixed length binary words, for instance values between minus 128 and plus 127. Yeah, so the values RGB are intensity values and hence only positive, right? Unsigned integer 8-bit. So here 8-bit integer values and the range between 0 and 255, and in Python this is called uint8. So this is what we saw. So the same is true for the luminance. The luminance is also positive, again between 0 and 255. But CB and CR now can have negative factors from the matrix calculation, and hence their values can also become negative. Right? When you look at this matrix here, we have negative entries, so the output can be negative too. So that's why their range is now signed int8. So instead of now going from 0 to 255, it goes from minus 127 to plus 127, or minus 128 to plus 127. So in Python it's int8, so without the u. Right, so this is something to keep in mind, that CB, CR now have a different number type. It has a sign. So in the decoder, as I mentioned, we can simply invert this matrix to get RGB. Right, so in the decoder we get Y, CB, CR from the encoder, then we multiply it with the inverse matrix, and then we get RGB. And here you can see the inverse matrix. Right, you can simply type it in Python and use the matrix inverse to get this. Yeah, and in this way we obtain one intensity component and two color components which contain all the information of the image. Yeah, so here's a Python example. We compute the Y, CB and CR components, or YUV in the non-normalized case, which is usually analog TV. And yeah, we compute them by applying the above matrix multiplications to each pixel of our frame. It is best to avoid for loops in Python because they are slow, but instead we compute with entire images, so that's convenient. So the computation of the Y image in Python is then simply 0.299, this factor from our transform, and now we multiply it with the entire frame for red. Right? So this R contains the entire frame for the red component, and similar for the green and the blue components. Right. So here the entire contain the entire images or frames. Yeah, then we can display the resulting U, Y, UV or Y, CB, CR videos as intensity frames again. So we can start the program in a terminal shell with the command videorec proc YUV, but first I need to edit it to change it to my new camera and also to show you how it looks like. So again, open it in an editor. So here you can see it. It begins as before. It just opens on different windows, but now with different names. Reads from the camera. Here I need to change it to number 1. Here you can see the conversion to Y. And here you can see frame. Here colon, comma, colon means the entire frame. 0 means component blue. That's why we have this factor here. Index 1 means component green with the corresponding factor. And finally here, index 2 means component red with the corresponding factor. Here I normalize it by 255 to bring it in the range between 0 and 1, float range. So Y is then float between 0 and 1. And this is because imshow, if it sees floats, it expects this range. Right? So this is a peculiarity, again, something you need to keep in mind. If you give imshow a float number or a float frame, then it expects the value range from 0 to 1. Otherwise you have it all white frame. Yeah, similar for the U and V. Here you can see this frame blue minus Y. Here's frame red minus Y, and the result is U and V. So basically, like the matrix is doing, just in a different formulation. And then here we display the different components. So, and finally, we keep it open until I press the key Q. So let me start it. So Python 3. So hit return. Oh yeah, this looks interesting. So here you can see the luminance. So Y is basically black and white version. So basically our artificial rod output. Here's the original. So you can see this is actually quite a nice black and white version of me. Right. And then you can see here the color components. First look at the background. So the background is basically white, and white is no color, and that's why it appears basically as black. So here you can see there's nothing, because the color components only become active when there's actually color. And that's done on purpose, because this makes it easily backward compatible to the old black and white TV. So in the analog time, it was important to have this backward compatibility. So and also it makes sense because when you have black and white, this is not really any color that you can distinguish. So there's no output for the U and V when you have no color. And you can see my face is kind of reddish, so it appears in the color component V and a little bit in the color component U. And you can see my shirt here is blue, so that appears more bright in the color component U. You can see the color component U is reacting more to the bluish tones than the red ones, and you can see the color component V is reacting more to the reddish tones or colors than to the bluish ones. Right, so it makes sense. So the color components really tell you what tone you have, what tone of color, and Y gives you the intensity, the black and white version. And then we can use this to code Y with higher resolution than U and V. So let me close this. Yeah, so this works nicely. Right, so anything not colorful appears as black in U and V. And here's also an interesting example for switching on and off the Y and U and V components. So let me first open it. So here we can see how they would change the output of the decoder if one of the components are missing. So here, let me first open it, the editor, gedit. So basically it's very similar to before, except that I here also have a decoder. So first here's an encoder where I convert from RGB to YUV as before. And here I have a decoder. Right, and here I convert from YUV back to RGB. So basically like in the matrix, just here in a different form. But it's basically the same thing. And in between here, I allow to zero out some of the components. So here I have different flags, Y on, U on, V on, and they allow me to zero out some of the components, except for Y. Y is not really zeroed out, but it's kept in the middle, so it will be set to 0.5 to avoid negative values for the RGB. Yeah, so here's then the reconstruction. Here it displays a little description of the keys that we can use. So here I assigned the keys U, Y, U and V to toggle on and off the different components. And I do that with the wait key. So the wait key allows me not only to capture the Q, but also other keys, which I did here. And each time I press one of those keys, it toggles the flag from true to false and back. Yeah, and again I need to change the video capture here. Go to 1, and then I can execute it. And then we can see the effect of those different components live. So Python 3. So now it starts. Here you go. Right. So here's the original, and here's the reconstructed. And here you can see the description. So now I can turn U off and V off, and you can see I have the black and white version. Just the Y is there. And you can see your eye can detect all the details the same as in the original version. Right. But now I can do the reverse. So I can now turn U on, V on, and Y off. So now only the color components are left. And now you can see this version looks much more blurry. Right there, your eye cannot see any details anymore. And that's because your eye doesn't have as many cones as it has rods. Right? Remember, if you're only having color information, here we have no information for the rods, then your eye acts like a 6 megapixel camera. Right? So it's much less resolution. So now it shows you that indeed the U and V components, which now only are active, can indeed be encoded with a much lower resolution without the eye noticing, because the eye doesn't see that much detail anyway. Right, and now I can go to a single color component, turn off V. So now you can see just U. U is bluish greenish, as you can see here. And now go to V, so turn off U and turn on V. And you can see the V component is reddish greenish. Right. Yeah. Okay, close this. So this shows the effect of the different color components. Yeah, and this actually lets you experience why indeed we can encode U and V with much less temporal resolution. We can downsample by a factor of 2 horizontally and vertically, for instance, and have by a factor of 4 reduced number of pixels, which means we have many fewer bits that we need to transmit. Yeah, and to show you that this is not possible with the original color components, we can try this Python example, which simply does the same except for the color transform. So first, let me open it with the editor. So here you can see it. So let me change this to camera number 1. And this is basically exactly the same, but now there's no color transform. So what I'm doing here, now I'm assigning the keys RGB to the RGB components and then do the same thing. So let me start this using Python 3. So, right, so on the left is again the original. Now I turn everything off. Green is off, blue is off, just red is left. And you can see, your eye sees still the same details as before, right? It doesn't really change the detail. Now go to green, same thing. All the details are still there, so if you would downsample just in the green component, the eye would easily notice. Then turn that off, turn blue on, same for blue. Blue appears now more dim because our eye is less sensitive for blue, but still all the detail is there because the rods are still active. Right? The rods are also active for blue. So let me turn this off. So this shows that it's important to apply this color transform. Right? Without the color transform, we cannot save bits on the colored components. Yeah, so we all have the same spatial resolution. Yeah, so now we can use it for reducing the spatial resolution for our color components. Yeah, and here you can see a few schemes for the color components which are usually used. So there's actually a numbering scheme here which you can see. So this example here shows when there's no downsampling. So the number refers to one row basically. We have one row which contains 4 pixels for Y, 4 pixels for CB and 4 pixels for CR. The next one is 422, which means we have in this one row we have 4 pixels for Y, but only 2 pixels for CB and 2 pixels for CR. Right? So we only have horizontal downsampling. But it also makes sense to do the vertical downsampling, and then the numbering scheme doesn't really fit anymore, so people came up with the idea to just say 0 at the end. It's not really so logical, but this is naming convention. So here we have 4 pixels for Y, 2 pixels for CB and 2 pixels for CR, and that is horizontally and also vertically. So 420 means downsampling by 2 horizontally and vertically. And this is, at least in the digital domain, the most common format. So if we do coding, compression, video compression, then usually we have 420. We can also shift it a little bit, but it doesn't really make a big difference. Yeah, so I have this from this Wikipedia page. So 422 is used for higher quality of video, for instance in studios. 444 is used for highest quality video, for instance raw or lossless formats. And when we do compression, it's usually 420. Right, and this 420 means we have a factor of 4 reduction in the number of pixels for the color components. Okay, yeah, I think this should be sufficient for now. I will continue in the next video with downsampling, upsampling and filtering. So thanks for your attention, and yeah, see you next time. Bye bye.